Welcome to session. Today we will discuss further topics in light. The next topic is principle of reversibility of light. We have seen how light behaves when it travels from one medium to another. What are the aspects of refraction? We have also what are the relationship between various properties of light, that is lambda, wavelength, mu, refractive index, velocity v. We have seen all those things. Now, today we will discuss principle of reversibility of a light ray. Now, see the screen here. There are two mediums, medium 1 and medium 2, and the light ray is incident in medium 1. Okay, it makes an angle of incidence I. Then when it enters the medium 2, it gets refracted along this direction, and it moves because the medium because the speed of light in medium 2 is different, so it gets refracted. As it is moving towards normal, it is obvious that medium 2 is denser. So here, if we define the refractive index of medium 2 with respect to 1, that is 1 mu 2, how will you define as per Snell's second law? Sin I by sin R, where I is the angle of incidence, this one, and R is the angle of refraction, this one. So mu 1 2 is given by sin I by sin R. So this is already known to us, and we are comfortable with it. Now, what if I make the light ray move in opposite direction? That is, the incident ray is coming from here, from medium 2, and is getting refracted in medium 1. This is the refracted ray and this is the incident ray. The angles are same, like R, because we are taking incident ray here. Medium 2 is the incident medium. So here the light is traveling through medium 2. This is the point of refraction, point of incidence. Then from here the light ray is getting refracted in medium 1. Now the angle, if we take angle of incidence as R, whatever is the angle of refraction here, if we take the same angle of incidence R here, then the refracted angle would be I. That is the principle of reversibility of path of light. So now here, suppose we call refractive index of medium 1. So here, refractive index of medium 1 with respect to 2. Here it was refractive index of medium 2 with respect to 1. So refractive index of medium 2 with respect to 1 in the earlier case. Here refractive index of medium 1 with respect to 2. So mu 2 1. So here, as per the Snell's second law, again this ratio would be sin R. Here angle of incidence is R, and then angle of refraction is I, sin I by sin R. Okay, so this is another expression we got. So far so clear? So now, what if we multiply refractive index, this refractive index and this refractive index? See, mu 1 2 is this refractive index into mu 2 1 is this refractive index. So mu 1 2 is sin I by sin R, and mu 2 1 is 2 mu 1 is sin R by sin I. So if you simplify this, sin I gets cancelled, sin R gets cancelled. So this would lead to, so refractive index of second medium with respect to 1 multiplied by refractive index of first medium with respect to 2 is equal to 1. Okay, so from this expression we can derive these two. So refractive index of 2 with respect to 1 would be inverse inverse of refractive index of 1 with respect to 2. Refractive index of medium 1 with respect to 2 is inverse of refractive index of medium 2 with respect to 1. Is it clear? Now, for example, if I say refractive index of glass with respect to air, that is mu g a mu g. Refractive index of glass with respect to air is, suppose it is 3 by 2, that is 1.5. So if it is 3 by 2, then from from this rule, like from these rules, we can easily derive refractive index of air with respect to glass would be 2 by 3. So inverse of this, because see, one refractive index is inverse of another. So here also, if glass refractive index is 3 by 2, then air's refractive index would be 2 by 3. Clear? So what is principle of reversibility of path of light? The path of light ray is reversible. So if this is the initial path and this is the refracted path in from medium 1 to 2, if I reverse the direction of light ray, if I send it along the refracted path, which becomes incident path, then it must go along this path only. So whatever is this path, okay, suppose we say A, B, C. So if we say incident ray is BA and refracted ray is AC, if you make incident ray like along the direction CA, then refracted path must be along the direction AB. So this is called path of principle of reversibility. Okay, let's move to the next topic. Now see on the right side of this box. Okay, so this is experimental verification of laws of refraction. What are the two laws of refraction? One, Snell's law. What are the two Snell's law? One, incident ray, normal and refracted ray at the point of incidence, they all are contained in one plane. That is first law. Second law, the sine of angle of incidence to sine of angle of refraction is constant for a given pair of media. This is second law. So these two laws we will prove experimentally they are true. So for this experiment, let us consider a plain paper. So take a plain paper and fix it on a drawing board with drawing pins. On that, you place a rectangular block of glass PQRS. Okay, and then you draw the boundary of that rectangular block of glass PQRS. Then remove that rectangular block of glass. So you will get a rectangle PQRS. Okay, so approximately around the midpoint of PQ, draw normal N and name it point O. So at point O, which is approximately midpoint of PQ, draw a normal N. Okay. Now, from the point O, that is from the point O, draw AO, the line AO, making at an angle of incidence I. Take an arbitrary angle, say 30, 40, whatever. So, using a protractor, you draw at an arbitrary angle I, you draw OA. Okay. So this AO, it represents the incident light ray. Now, at 2 points, which are shown, this is B. At 2 points, AB, take two pins and pin them on the line AO. So at point A, one pin, and point B, another pin. Okay. Now place the rectangular slab again on the rectangle, exactly matching with the boundary. Okay. Now you go and watch. You go and watch, like from here, that is here. You try to look at the drawing pins that are fixed on the other side of the rectangular block. So you will see the pins, the image of pins somewhere. Okay. So wherever the first pin is there, wherever the image of first pin is there, you put another pin at point C. So C is the image of pin A. So from looking from here, while you are matching that pin, you press another pin at point C. Likewise, for pin at B, the image that is matching with pin at B, you put another pin at D. So when you are watching from this side, all these four pins, 1, 2, 3, 4, will appear to be in a straight line. Okay. So now remove the rectangular glass block, and then join these points C and D with a scale, and let this line intersect the line SR at point B. Okay. Now this CB would be your refracted ray. Because you have point B now, join O and B. I'm sorry, BC would be your emergent ray, not refracted ray, emergent ray, and the point OB would be your refracted ray. Okay. So now AO would be your incident ray, OB would be your refracted ray, and BC would be your emergent ray when you are watching from the point C with naked eye. Okay, so far so clear. Now, after extending this normal onto M, using a device, we can measure the angle R that is made here. So that would be the angle of refraction. Okay, so angle I is the angle with which you had drawn the line OA initially. Some arbitrary angle you took already. Then you got angle R. Okay, so because you have angle I and angle R, so you can find out sine I and sine R values from sine table book. So you can get this value and this value from sine trigonometric table books when you know angle of incidence I and you also obtain angle of refraction R. So you will get sine I and sine R. Then in this column, when you are taking the ratio of sine I to sine R, this ratio is giving you the refractive index of the rectangular block of glass. So this experiment, like when you initially took arbitrary angle of 40, so you can take various arbitrary angles, say 50, 60, 70, 80, as many angles as possible and as many readings of R as I as possible, and then you obtain corresponding readings of refraction. Then if you tabulate in this table, so you will get various values of refractive index of the rectangular glass block. If you take average of it, that will give you the refractive index of the rectangular glass block. Now when you do this experiment, we see that the sin I by sin r, that is mu, is almost constant. It might vary slightly, but it is almost constant. So that proves our Snell's second law, that is ratio of sine of angle of incidence to sine of angle of refraction is constant for a given pair of media. So here glass is the second medium, air is the first medium. So for this given media, the refractive index of the glass with respect to air we have obtained experimentally. Clear? Now, if there are no trigonometric tables available, so you don't want to look at the trigonometric tables and arrive at the values of sin I and sin r, there is another method in which you can obtain sin I and sin r. From point O, that is point of incidence, draw a circle with a suitable radius, appropriate radius, somewhat. It should cut the incident ray at D, then it should cut the refracted ray at E. Okay, if you draw such a circle with O as center, which will cut angle of which will cut incident ray at D and refracted ray at E. Now, what we can do is draw a line parallel DF that intersects the normal, the parallel to PQ. Okay, or you can say this is perpendicular to the normal. Here, draw a horizontal line perpendicular to normal G that is parallel to again PQ. Now, if you measure the DF and G, so this ratio DF by EG or GE, like this distance DF by EG, this ratio will also give you refractive index of the rectangular block. So the summary of this experiment is, we are taking a rectangular block made of glass on a white paper. We are drawing its boundary PQRS. Okay. On the line PQ, approximately somewhere in the center, we are marking a point O. We are taking it as a point of incidence. From here, at point O, we are drawing a light ray in the direction AO, which is we are drawing a straight line with an arbitrary angle I, say 40 degrees, and then drawing the angle AO. So AO would be the direction of incident ray. Okay. Now we are fixing two pins at A and B on the line AO, and after placing the rectangular block in its position, we are looking at those two pins from the other side of the block, and we are trying to fix another two pins at exactly the place where their image is formed. So these two pins are fixed at C and D while you are looking at actual objects at A and B. Now you can join a straight line connecting these two pins and extend it as BC. So this BC line, which intersects the boundary of the rectangular block at B. So now we have point A and point B. If you join, this would give you refracted ray OB, and BC would be the emergent ray. So once you get the angle incident ray, refracted ray and emergent ray, you can measure the angle of refraction R. Either you use the trigonometric tables and to find out the ratio of sin I by sin R, or you can draw a circle with O as center, which cuts the refracted ray at E and which cuts the incident ray at D. Then at D, draw a horizontal line parallel to the boundary PQ and draw another line at point E, which is parallel to again PQ. So if you can measure these two lines, DF and GE, the ratio of DF and EG would give you refractive index. So this proves that the ratio of sin I by sin R, if you see your values after experiment is done, your observation would be like this constant. So sin I by sin R is constant, and that indicates the refractive index of glass. Okay, so the Snell's second law is proved to be true, or we can say Snell's second law has been verified. Now Snell's first law, see, the angle of the light ray, incident light ray AO, refracted light ray OB, and emergent light and the normal ON, they all lie on the white paper, which is the plane. So that proves Snell's first law. Hence, both the laws of light, that is Snell's first law and second law, have been verified. Okay, let's move further. Now, this experiment is very similar. Okay, so likewise, here also you are taking a rectangular glass block. This is your incident light ray. At point O, you are drawing normal NM. Refracted ray, the light ray is getting refracted along OB, and then when you see from this side, OC would be your emergent ray. So incident ray AO, OB refracted ray, emergent ray BC. Angle of incidence is I, angle of refraction is R, and here is another angle, theta. So this is called angle of emergence. Okay. Now the same phenomenon, whatever we had done earlier, the same phenomenon. See, the path OD would have been the original path of incident ray if there were no refraction. So for a person who is looking from this side, okay, so the incident, there is a shift in incident ray, although emergent ray. Although emergent ray is moving exactly in the direction of incident ray, but they are not moving along the same line. So for an observer at this point, he 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 observes that there is a lateral shift of x in the incident ray when he is observing from this point. So this lateral shift is called lateral displacement of light ray. Understood? So the same experiment, verification experiment. So when we are observing from here, for an observer, this incident ray appears to have shifted laterally by a distance x when he observes from this point. This phenomenon is called lateral displacement of light ray. All other parameters are same. Whatever we had covered in the earlier verification experiment, it's almost same. Now here, what are the factors on which lateral displacement of light ray depends? First thing, observe. Suppose I increase the angle of incidence like this. So I am increasing. This is the angle of incidence. So my reflected ray would move more closer to angle. more closer to normal. So what is happening to lateral shift? The new lateral shift is this one. So this lateral shift is greater than this earlier. So what is your observance? If the angle of incidence increases, the lateral displacement increases. That is first. Second, sorry, that could be second, actually second. Now, suppose I increase the thickness of this rectangular block, and this is my new boundary. So what will happen? The refracted ray will come here. So you see, here, so the lateral distance will increase. That means if the thickness of the rectangular glass block is increased, then lateral displacement would also increase. That is second point. Third point, see, we have seen earlier vacuum, air, and so on, the densest medium and down. So as we go from top to bottom, we will decrease. Okay, and wavelength will also decrease, but refractive index will increase. This is what we observed in the spectrum of optical media. So from top to bottom, when we are moving, velocity of light, wavelength of light, they decrease, but refractive index will increase. So the same analogy applies here. When the wavelength, when the velocity or wavelength increase, okay, can you see here? If the wavelength and velocity of light decreases, x increases. So as we move down, so lateral displacement increases. So you can remember in this way. As we are moving down the spectrum from top to bottom, lateral displacement would increase. That means if the velocity is decreasing or if the wavelength is decreasing, the lateral displacement would increase. So these are the three points on which, factors on which the lateral displacement will depend on. So now what is the, let us summarize what we have seen. So using a rectangular block of glass, the incident ray, when it is observed from the opposite side, okay, so the emergent ray and incident ray, although the direction is same, the emergent ray appears to have laterally shifted by a distance. This is called lateral displacement of incident ray. This lateral displacement depends on three factors. One, if the thickness of the block increases, lateral displacement increases. Two, if the angle of incidence increases, lateral displacement increases. Three, if the velocity or wavelength decreases, lateral displacement increases. Or in the optical medium spectrum, as we move from top to bottom, lateral displacement increases. Okay. Now, suppose this is a very thick mirror. We are doing multiple reflections in a thick mirror. This experiment we are doing. So, assume there is a light ray actually there is one. Okay, we'll stop it here.